theory seminar. Today we have really a very special guest from the US, but a person that really bridges the gap between China and the US. Professor Weimin was born in Shanghai and got his bachelor's degree from Fudan University, famous university in Shanghai. And he received his Doctor of Science from Lanzhou University in middle of China. And Doctor of Science here is sort of the Russian system. Okay? And before he got his degree in nuclear physics. And he's very proud that actually he participated in the Chinese nuclear bomb. And in the 60s, it was the Cultural Revolution. So Lanzhou University was taken over by actually the ballistic missile troops. And that became another element of his career path, that he actually spent 10 years, sort of modeling trajectories of ballistic missiles. That's what the purpose is. And then, in the late 70s, he volunteered to join the High Energy Institute in Beijing of the Chinese Academy of Sciences. And a few years later, he was sent to CERN for 2 years, 1979 to 1981, and returned to Beijing as a rising star, I would say, at IHEP. Groomed to be, and 83 to 85, he was on another stay at CERN and got heavily involved in Aleph and became the deputy, deputy group leader. But both in charge of both the best experiment at its formative stage and also Aleph, so very international. But then came 1989, so that's another big change in his life. So because June 4th is coming up, after June 4th, because of his special connections and opportunity, he left China and first stayed at CERN for more than half a year. And in 1990, he first went to Argonne and joined SDC with the SSE effort. So at that time, that was the big collider under design. In 91, he moved to 92. 91 he moved to Fermilab. First as a guest scientist, and then he stayed on at Fermilab up until now. But Fermilab is under restructuring. So anyway, we don't need to go into that. So I would say it's both an illustrious career and certainly an extremely rich one. He has already written a book that's somewhat more related to photography as well as physics. And he's currently finishing a book on his life stories. So it's actually an amazing story, but he's actually a real physicist. So he has been a member of CMS just like myself, and he's going to report on the work he has guided a student to do in CMS for heavy Majorana neutrino research at CMS. Okay, Professor Wu.
Thank you. So, my life is very strange, and this is the last research I have done during the last few years. Actually, start from 2008. We already do the Monte Carlo study on that. And at that time, I only had one student from Iowa University who did the Monte Carlo study from 2008 until last year. He graduated from Iowa University, the PhD, and based on this research. And then I had another student, which is Wu Yifan, and he is from Beijing University, and he is going to be PhD defense in about 2 weeks in Beijing. So after that, I'm going to there. And the first student is doing Dielectron, which is muon. And this lecture is based on the Dielectron. So it's slightly different, but the philosophy, everything is the same. And we're using 2012 data, 2011 data, and we published this paper. So this result, the presentation is based on basically on this paper and only focus on the electron channel. So here's a brief introduction. And I'm not a theoretician, so I'll very briefly talk about why we want to study, what is the motivation, and how to generate a signal, and how to estimate the background, and what the result, what is the new in our result compared with the previous result. And in the end, also briefly talk about the result from 2012 data. So why I want to get the Majorana neutrino study? And the reason is that we come from why the neutrino has mass is very certainly seen. We not only know the neutrino has mass, also know neutrino has mixing and so on. But how to explain why neutrino has mass? And there's a leading serial mechanism which is called seesaw mechanism to explain that. And which means by introducing one of the neutrino, heavy neutrino, and there's explain why the neutrino has a small mass. And one of the important advantage of this study is actually the cross-section for this mechanism is not very small. In order of fingerbar, the order of fingerbar compared with a lot of really physics channel is not so small. And if we look at the cross-section, we can basically divide it into two sections. One is model independent, which is called barrier cross-section. Another is flavor dependent, which is a mixing element between neutrino and Majorana neutrino. And this barrier cross-section only depends on the accelerated central energy as well as the mass of the Majorana neutrino. And this one is only depend on the flavor of what lepton flavor is. And so far, before us, in the accelerated experiment, only lab L3 and Delft has set a limit is about 90 GeV. And we are focused on to beat the lab result. This is our purpose. And many people already talk about, I believe, what the LHC, what the CMS, and so on. And so I don't really talk about detail about that. And we analyze 2011 data and 2012 data. And all the trigger available for us is 2011 only 5 inverse figure and 12 has 12 inverse figure. And this detector is most of people think National Taiwan University deeply involved the CMS construction and the detector design and so on. And I believe people are familiar with that. And for this part, I only tell you a little bit small story about that. And people very funny. What is the graduality for the H curve is 0.087. And where is this number from? Very funny number, the gradularity of the H curve. And at the beginning, actually, if you look at our conception design, it's 0.05. And at that time, CMS decided to using crystal for the E curve, which costs a lot of money. So where did the money come from? So then we try to reduce, make the H curve a little bit loose. So if rising from 0.05 and increase to 0.1, up to which limit will not compromise the H card is losing, but still can do the good physics, but also can save a lot of money. So at that time, actually, I did a lot of simulation study, and make the curve water gradient from 0.05 to 1, and find out up to 0.0875, and H card dielectric resolution is almost the same with 0.05. So finally, we decided using 0.0875 instead of 0.05, and save money for the E-card. Actually, save about a few $1 million, and this money supporting we make a very better E-card. This play important role for the Higgs discovery this time actually. So this is small story behind. And another is this part is talk about the muon chamber system. You will see our CMS is a compact muon solenoid detector. So very good muon measurement is our key element. And this small story behind it is China. It's IHAP is built about almost half, between 1/2 and 1/3 of muon chamber is built in IHAP in China. And the reason behind that is because China already built one with the Aleph group leader in China, and we already built half of the Aleph muon chamber by IHAP. So IHAP has tradition to make muon chambers. They have mechanism, workshop, and the measurement equipment and the expertise. So. And why choosing this channel? And there are many reasons. And one of the reasons is our actually the study is proposed by Han Tao, who is a friend of mine. And at that time he is a Chinese from Nankai University. Now is I think the director for physics in Pittsburgh University. And he proposed me. I had done several studies with him together, including little Higgs, black hole, and so on. And he suggests me take something to do that. There are several reasons. One is the important to cross-check of the mass limit for neutrino and Majorana neutrino. Because the seesaw mechanism, so the neutrino mass is related to the Majorana neutrino. So if we can set up the Majorana neutrino mass limit, so we can cross-check with the neutrino mass limit. So this is significantly important. Another is this process is same sign dielectron or diemuons and so on. And this is can deeply suppress the standard model background because a 2CD background because it's a lepton number violation process. And also in this process, no missing ET in the final state. So this also can suppress a lot of SUNY background. And for this reason, he believes we probably using LCC can get a much better result. And unfortunately, at the beginning, his paper is based on 14 TeV. Now became the 10 TeV. Now finally, we even not 10 TeV, only 7 and 8 TeV. So cross-section get smaller, and also we did not really get about more than 30 even the Fermilab data, only altogether less than 20. So nevertheless, at the beginning we thought probably we had no chance to do anything, but still, finally we still get some set some limit, and this is what the best we can do. But people in IHAP and the CMS decided to continue to do this research in after 2015, and including email channel as well. So this is the signal production, and here is we started with, as I said, starting in 2008, and at that time we using the Han Tao's mature element program, and we generate those events ourselves, and we published several Monte Carlo papers on that. But since we have data, and the CMS is not allowed using the private event generator, so have to use the official one. And then we talked to the author of Origin. Finally, they installed some kind of key code from Hantor and in the official of event generate, and we produce different energy and different mechanism on this event generator. Finally, our paper is agreed with these two different cyclocity, either from origin or from Hantor's paper. And here is the just giving you an impression about how about the Monte Carlo for the signals, and Monte Carlo electron and jet PT distribution and ET distribution, eta and so on. And one thing I just want to mention that we make an unsymmetric cut. So because the leading jet and the leading electron, the distribution quite different from the second leading electron or jet. You can see that. So we make unsymmetric cut. And here is a signal Monte Carlo example list. We generated the file from...
The CMS paper is only on dielectron?
Oh, no, both.
Dielectron,
Electron and diamine. Yeah, actually both. Yeah. For the before, actually only diamine for the Monte Carlo study. And the paper itself including muon and electron. But we are halfway go to electron E-mu channel. Because in principle, dielectron channel can including EE or mu or E-mu and E-tau and so on. And tau is more difficult, so we sort of we give up. And the E-mu we did not finish. The reason is we have to study the correlation between E and mu, and which is quite difficult. And besides, not enough manpower because one of the students from our already graduated, another one he's not going to do physics anymore. He's not willing to finish E-mu channel. So after he gets a PhD next month, and he will go to some business area. So he's not very motivated anymore. So this is another story. But anyway, and so for this study, it's very important to identify what is the electron. And we have using different way to identify what is the electron. First, we check the information from ECAR. Then we have to match the vertex and the track. So only if they can from 3 different systems to match together, then we can identify this is the real electron. And so I'm not going to tell in the detail about that, but identify electron in the CMS very mature software to identify them, and we just determine what kind of parameter your requirement and so on. Afterwards, I will mention a little bit detail. And then the important thing is and here the jet. The jet is also using standard CMS produced the jet in our database. And the algorithm is anti-KT, and then we have different sort of jet, either the color jet or truncated or particle flow jet and so on. And we actually using all of them to combine to see what is the real jet. And the trigger is, since we have to have 2 electrons, so we have the double electron trigger database. But also we need, later on I will talk about what the background, and the dominated background is a fake background, fake electron, which is from jet, misidentified as a jet, as an electron, or some from the electron like from B quark decay and so on. Those became also misidentified as a real electron. And so we need some single electron data set to test our fake rate algorithm. And so this is the file we have used. And here is the even the trigger, as I already mentioned, is using 2 electrons, and then they have this is from different run, and also have different unsymmetric, like this one using 17.8 or this is 17 is 8, and there's another. It's not in our hand because we are a small group, and our voice to influence the trigger condition is very limited. So we only can pick what they already provided. And primary vertex is very important for our study because number one, we want to make sure where is the electron from? Is from the secondary decay or from the real the vertex origin from the interaction? And another thing is we want to separate the pileups, so we also need a very precise measurement of this vertex measurement. Another thing is we have to in the pileup collections also we need very detailed information about the vertex number of vertex and so on. There's another thing. Even this is the electron channel study. We still have to reconstruct the muon, identify muon, and so on, because the electron, if the muon also can be misidentified as an electron. So we have to find out what is the good muon. Then if there's some electron which you found very nearby to the muon, it could be confusing. So this event also, those event electrons, we also have to remove. So now come to the detail of electron selections. First of all, as I already said, is unsymmetric cut, and then the AW region, and also what the primary vertex, and isolation required, and all this, and also we have to require the non-missing hit in all the particle flow region and so on. And then in the Dielectron group, they're also developing this kind of stuff like a black box. Inside this black box, there are a lot of very special parameters. It's for people to use to get a good quality control of electrons. And for the jet, and at the beginning, we only using 20 GeV jet for the jet cuts. But finally, the reason is because we want to keep more events in the low mass region, because Delphi and L3 already set the limit in the 90 GeV. So we want to, at that time, we did not have much ambitious. We just want to beat the left result. So we want to try to get as much as even possible to make a very loose cut. And finally, when we learn to the 2012 data, so we probably have more data. So we write in the high, the jet PT cut from 20 to 30. So make more extended to our limit to the more high mass region. But after we publish our paper, Atlas do exactly as we do, but using the cut became 40 GeV. So they extended the limit to about 300. We only set to about 200. And because Atlas want to beat our result, our result only set up a limit to the 200. So they even get much less event, but they do extend our limit to the 300, which I will show you mixing element plot afterwards. Those other NCLs is almost very standard with other dielectron analysis procedure. And for event, we pick electron 2 and only 2. If there's a third electron satisfied with this condition, we just veto it. And since our final set has more than 2 jets, and we also take at least a minimum of 2 or more jets, and taking using 2 leading jets as our final jet to reconstruct the W. And for lose this selection for the low mass only about 1% efficiency after all these cuts. For high mass it's about 20%. So it's already losing a lot of money, losing a lot of efficiency. If we get more tight cut, even worse. That's why when we see the Atlas paper, they put a 40 TeV, and here is only about 10, here is about less than 0.1%. So the background. At the beginning, I said that the advantage of this process has very little standard model background, and also has non-missing ET, so very little SUDI background. But actually, the our background has several sources, particularly is the last one. Standard model background, very little. And from this secondary from electronic decay from B or whatever, or like this process produce a lot of leptons, the crucible is cannot pass the selection procedure, and also possible defilling through to some geometry gaps and so on. So finally also can produce two same sign lepton which survive. But those can be estimated from Monte Carlo simulation very well, and also is very small when we see afterward. Another is electron charge misidentification. Although CMS is very good software to determine what is the charge of electron, but still about 0.1% of misidentification rate for the dielectron channel study. For muon, it's almost 0.0001%. So it's not a problem. But for electron, it's quite a problem if we misidentify the charge. So the different, the opposite sign can become the same sign. So this is another background. And the most important background is jet, or some secondary electron identified as a fake electron. And those are the dominant background in our study. And before the Monte Carlo study, we don't using this sort of fake electron algorithm. But now, since the SUDI group and some CMS says about more than 20 people, they spend years to developing this kind of fake rate algorithm. And so finally, they decided anybody using dielectron study have to use this algorithm to estimate a fake rate background. And before, actually, if you look at our Monte Carlo paper, we're using like ABCD method and other method. But now this part became standard of CMS paper.
Yeah, earlier you talked about also muon selection. So it was only to reject some events or what?
Yeah.
What type of events?
If actually it's muon, it's not an electron.
Yeah, I know, but you mentioned selecting muon and rejecting something within some radius of a muon. So what was that?
Yeah, if actually it's a dimuon events, one actually is not an electron, but it's a muon. And this channel we studied dielectron. So if in principle, in our study, we don't care about the muon. We don't need selecting muon because it looks like a waste of your time.
Right, but you discussed muon selection, there were some words in earlier pages about muons, but now you're focusing on electrons, yes, but I think in your event selection you talked about muons.
Okay.
Previous page?
Yeah, muon selection.
So why was this relevant?
Oh, because it's we have to further
for background study.
Yeah.
Okay.
Yeah.
But it's a probably minor background.
Very minor.
Yeah.
Very minor.
Okay. That's part of the conclusion.
Yeah. Okay. Sorry. Okay. So this is three types of background. For the Monte Carlo and the standard model Monte Carlo, this one we purely using Monte Carlo. Just we generate some events, and then just to see what the Monte Carlo truth, what we found, and so on. And so this is easy part. And finally, also we found that this is very small potato compared with other background. And the standard model source, we produce a lot of stuff here. And actually, at the beginning, we only have W0ZD, this kind of stuff. But then, in the very complex the publication process, people always ask, how about this one? How about that one? How about that one? Then we always have to follow their instruction and produce more and so on. Finally, actually, really small contributions. Yeah. And for the Monte Carlo, one of the things is very important is pile up collections, because in the Monte Carlo general events, the number of vertex is constant. There's not such information. In the real data, we have to have, for example, collecting it has a distribution, and from 1 to 20, and then maybe pick at 5 or 6 or whatever. And then we have to reweight them. This is one of the things in the standard model background we have to do. And for the mischarge, mis-ID, and this is called half data driven, half using Monte Carlo. And here is the method. First, get the charge mis-ID from the electron down. So we produce some Monte Carlo event with a certain charge, and we compare with data generated compare with the generated information and the contrast information. Then we find out some of them the charge is misidentified, get wrong. Then from this part, using so-called data driven to test whether this misidentification of electron is doing well. So what we do is create the control sample in our data. And by those selections, the environment in the ZMass window, and also has no missing ET if electron goes Z equal to E, and all this kind of requirement. So we think in this region,